So today in this lecture we are going to talk about the one-dimensional finite element program. So before we write the one-dimensional finite element program, we have to fix what should be the features of the program. That is, what should the code be able to do and what kind of material data, loading data and boundary conditions it should be able to handle. So let us take as an example the following case. So this is our member with this line being the line of symmetry, or we will call it the x-axis. Okay, so in this member now I can have a material in this region and some other material in this region. So here we would like to have material constant E1 and the area, if you see in both the members, is tapered but with different taper ratios. So here I will say the area is A1 of x. Okay. In this member, the material constant is, or the Young's modulus can be E2. Taper ratio is, or the taper is given by A2x. So this is what we would like our code to handle. Now, where this transition happens, this transition we are going to say is at the point xn. This can be point x0. This could be point x1. Okay. So we know that x1 is minus x0 is equal to L. So we are going to set our x0 to 0. So x0 we are going to set it to 0. Further, what other features we would like to have? So the other features that we would like to have, other features are the following. That I would like a distributed load along the center line with intensity f of x given by f0 plus f1x plus f2 x squared. That is, we would like up to a quadratic distributed load. We would like to add some more features to our program. Okay. We would like this program to be, if desired, on elastic supports. But what we would like is the elastic support should be distributed through the whole domain. That is, it should be applied to the full domain. Okay. And we would like this elastic support to have an intensity Kx equal to K naught. So our elastic support has uniform spring constant. We do not want the spring constant to be very different. It should not vary. Another feature we would like to add is, let's say there is a point here, okay, which we will call, the location of which will be given by xp. At this point, I apply a concentrated load of intensity P1, of size P1. So this is a concentrated load I am applying here of size P1. And what we would like our code to do is to handle only one concentrated load, not more than that. Okay. Further, now we would like our code to handle various types of boundary conditions. What could be boundary conditions? I can have here an end force Q, which is tensile here, while at the other end I could have the end force given in terms of the force applied by an end spring. Now, if it is a force applied by an end spring, for the spring I have to specify the stiffness coefficient for the spring and whether it is pre-compressed or not. Delta L that we say is an initial compression of the spring. Okay. This spring could be applied here, this force could be applied here, we could have any mix and match of these various kinds of boundary conditions. Further, we are also looking at boundary conditions which are geometric in nature, that is, we could fix this end. So we would like to handle all these kinds of boundary conditions at each of the end. I could choose any one of the three which is there. So this is the problem which we would like to solve. The order of approximation that we want is P, let's say, is less than equal to 3. If you look at this problem, as far as making the mesh is concerned, we have to honor certain boundaries. Which boundaries we have to honor? This boundary where there is a transition of the cross-sectional area or the material, we want both the transitions to be the same. Okay, we do not want separate. Another boundary is here. We have to put a node here because at this point a concentrated load is applied. So if you see, my mesh is broken, my domain is broken into these three parts. This part from x0 to xm, from xm to xp, and from xp to x1. So these are the three parts that we would like to handle. So let us now go and essentially look at how to design the preprocessor to handle all these cases. Okay, for the preprocessor design, we would like to first read the input data. Okay, this could be through a program. We can call it read data. One can name it whatever he wants to, but the name should reflect what the program is doing. So read data is our program. Now in this, what would we like to read in? First, we would like to read in domain data. From our figure that we have drawn there, this domain data means I am interested in the extremities of the domain. So x0 and x1. So x0, which for us is going to be 0, and x1, which is equal to the length of the member. Or we could have said x1 minus x0 is equal to L, but here we are setting x0 is equal to 0 and x1 equal to L. This is what we have to input first. Then we would like to input the material data. So how would your material data be read? In the material data, what are the things we have to input? So we have to input the values of E, E1. We want to also have the values of A1 as a function of X, okay, which we are going to give in terms of two parameters, A0 plus A1 into X minus Xm. Okay. So this is given in terms of A0 plus A1 into X minus Xm. So if I have to give this, then I have to also input Xm. So this E1, A0, A1 and Xm have to be inputted first. Next, we have to input for the second part of the domain E2. A2 as a function of X is equal to B0 plus B1 X minus Xm. So for the first part of the domain, we input these two things. For the second part of the domain, we input these quantities. So it will be better to first input the transition point Xm as a separate entity, and then for the two parts of the domain, we give E1 A1 and E2 A2. Okay. Now, in case I want only a single domain, material domain. For example, I take this bar, okay, for which my E1 is equal to E2 is equal to E, and A1 is equal to A2 is equal to A. It could be tapered, but the taper is not changing. So in that case, what will we do? We will make Xm, in this case, make Xm is equal to X1. If you do that, then what will happen? Your program is going to take only E1 and A1 throughout the domain, because the second part is essentially at the end of the domain, so this will not come into play. So these data can be inputted all the time, irrespective of whether I have a transition or not, and according to the choice of Xm, the appropriate data will be taken. Okay. Now, if I see this is given, now if I have Kx, we know we want it to be a constant, K0. So this also, K0 also has to be inputted as an input data. So as far as material data is concerned, we need to input the point of transition, Xm, we need to input A0, A1, B0, B1, E1 and E2, and K0. So totally we need 1, 4, 7, 8 data. So 8 quantities has to be inputted. This quantity is a user supplied quantity, because this is something that the user is telling that, okay, this corresponds to the domain, material data and cross-sectional data of interest to me. Okay. So once we have this, then once we have the material data, we would like to give the load data. What is it that we have to input as far as the load data is concerned? We have said our distributed load is defined over the whole domain. It's not defined piecewise. That is what we would like to use in this program. We could define it piecewise. That will only add a little bit more to the complexity. So here we want to define it globally, that is in the whole domain. So our fx, as I have drawn on the figure, is f0 plus f1x plus f2 x squared. So these quantities f0, f1, f2 have to be inputted. Now if I want a constant load, I will simply make F1 and F2 equal to 0. If I want a linear load, I will make F2 equal to 0. If I want no load, then I will make F0, F1 and F2 equal to 0. So this way we can get up to a quadratic loading as a distributed load that we want. What else do we want? We want to give whether there is a point load or not. So if there is a point load, we would like to know what is this point where the point load is applied and the value of the load P1. So both this data has to be given. Okay. Now if I don't want a point load, then in case I don't want it, then I will set P1 equal to 0 and I will set XP equal to X1. Okay. So what I am doing is I am going to make this value 0 and I am moving this point where this 0 load is applied, which is meaningless, to the end of the domain, just for our convenience sake. So you have to remember that when P1 is equal to 0, I will have to set XP equal to X1. We won't give XP equal to some point in the interior of the domain. So this data is available to us. So now we have the domain data, the material data, the load data. What else we need? We need the boundary data. Okay, because we need to specify the various boundary conditions, so let us now take end 1. This corresponds to the point x0. So if I take my member, what are the boundary conditions can I have at this point x0? So I could have 1, the displacement is given, it need not be 0, it could be some value. I could have a second candidate is the force Q is given at the end, and the third candidate that the end has a spring with constant K0 and an initial compression delta naught given. Okay. So we are going to call this, if you remember, we had introduced this as a Robin boundary condition, and the previous one, if I go up, this is Dirichlet, and this one is Neumann. So we have to have the feature that at this end I should be able to give any one of these boundary conditions, and along with this boundary condition type I should be able to input the data that goes with it. So here if I say Dirichlet means U0 is given as U0 bar. So let us say that we will specify the boundary condition type at N1 by the following numbers. It is 1 when it is Dirichlet. It is 2 when it is Neumann. It is 3 when it is Robin or mixed. When it is Dirichlet, we have to input the value at this end of the displacement, U0 bar. If it is Neumann, I have to specify what is this end load, which is Q is positive if it is tensile. And if it is Robin, then I have to specify what is the spring constant K0 and initial compression delta naught. Okay. So these are the information that we need to have at this boundary. Okay. Similarly, at the other boundary, so at end x1, which is, we say, so end x1 is given by the boundary node 2. We will say IABC type 2. This would be again 1, 2 or 3 depending on whether it is Dirichlet, Neumann or whatever, or Robin. So if it is Dirichlet, then at this end we have to give, it is U1 bar. If it is Neumann, then it is the end tensile load P, and if it is Robin, then we have to give the end spring constant K1 and the end compression delta 1. So all this data has to be inputted. So this has to be given, this has to be given, this has to be given, this has to be given. The type, the boundary condition type has to be specified at each of the ends. What is the type? And accordingly these data have to be inputted. Okay. Now let us, for completeness sake, specify what this means at the other end. So here I mean that when it is 1, then I am specifying the displacement here. When it is 2, I am specifying the end load P. When it is 3, then I am specifying the spring constant and the initial compression delta 1. At the end, x1. Okay. So as far as the boundary condition is concerned, this is the information we would like to have. Okay. So the boundary condition type and the corresponding data. So how do we input this data? We could have one input as the boundary condition type, the other input as the two parameters alpha and beta. Okay. Which for the Dirichlet type will give alpha equal to U naught. So at each of the ends, alpha is equal to U naught bar. For the Neumann part, at end 1 it will give me alpha equal to Q, and for the Robin it will be alpha equal to K naught and beta equal to delta naught. Similarly, I will do at the end x equal to x1. So at the two ends we have to give these two parameters, where the second parameter for the first two types is an irrelevant parameter, but anyway we can specify anything and it will not be used finally. Okay, so after I have inputted all this data, then I have to create some information. So some information which is needed. So out of, I would say that in the read data program itself, routine itself, we construct that information. So what is that information? The information is the following. Let's say this is my point x0, this is my point x1, this is my point xm, my xp could be here, my xp could be here. Okay. But I have to honor these transitions as we had said. So transitions means if my xp is here, then this is now a piece by itself, this is a piece by itself, and this is a piece by itself. So we have the three pieces which are given by, in this case, x0 to xp, xp to xm, and xm to x1. And the length will be given by L1, L2, L3, let's say. So these things, this information has to be available to us. Now, the computer doesn't know whether xp is happening before xm or it is coming after xm. Okay? So this information has to be created for the computer to understand that okay, these partitions have these points xp, xm and so on as the endpoints. So let us now find how can we do that. So we will find the 3 points. So x0 is fixed. We will say x1 is fixed, x2 is equal to minimum of xm and xp, and x3 is equal to maximum of xm and xp. Okay. When we say x2 is the minimum of xm and xp, along with it we will carry the flag whether this is a material point or it is a point of point load. Let us make that flag. Let's say that this will have an indicator, x2 will have an indicator I flag type. It is equal to 1 if this is xm, or it is equal to 2 if it is xp. Similarly here, we will call it I flag type 1. Here, for the max again, we will have a corresponding flag associated with it, I flag type 2. This is equal to 1 if this is the point xm, and it is equal to 2 if it is the point xp. This is going to be useful. This is a very trivial information that we are creating along with these points x2 and x3. It is going to be useful when we are further constructing the mesh and deciding the elements where they lie in, which material domain they lie in. Okay, so let's have this flag and along with this point. So what do we have now? If I look at my domain, I have the point x0, the point x1, then I'll have the point x2, and I'll have the point x3. And the flag tells me whether it is xm or xp, here and here. Okay, so this is the flag is telling me these things. But as far as the partitioning the domain is concerned, we have these distinct partitions. Now I will measure the length. L1 is equal to x2 minus x0. L2 is equal to x3 minus x2, and L3 is equal to x1 minus x3. These lengths we are going to measure. Note something, that this L1, L2 and L3 can each be either 0 or L. For example, if I say that my material point and both the material point and the point load are at x1, that is, I do not have material two material domains and I do not have the point load applied, in that case it will this x2 minus x0 is going to be L. x3 minus x2 is going to be 0, x1 minus x3 is going to be 0. So only L1 is coming out to be L in that case, and the other two things are coming out to be 0. If I say that my this point load does not exist, I only have a material transition. Then if I have a material transition, then I will only get, in that case I will get x2 is equal to xp, x3 is equal to x1. So I will get L1 is equal to x2 minus x0, L2 is x3 minus x2, which is perfectly fine, L3 is equal to 0. So I will get only the two partitions as such. Okay. So with this data, now do we have all the information that we need? Okay. We now need to give one more data, which is the mesh data. Now that we have defined the three partitions of the domain, remember these are not nodes, but these are the partitions of the domain honoring the material boundaries, the point of application of the point load, and the extremities of the domain. So it is x2, x3, x1. with length L1, L2, L3. Then we can ask the following question, that in each of these partitions, how many elements we need to put. This is an input data which has to come from the user. The user may decide to put different number of elements in each of the partitions based on his needs, based on certain a priori information that he has about the smoothness of the solution and so on. Okay? So let's say that in each of these regions we are specifying the number of elements we need, N1, N2, N3, and we are assuming piecewise uniform meshes. Okay? So what we are saying is, tell us as an input data what number of subdivisions you want in the first piece, which has length L1, in the second piece, which has length L2, and in the third piece, which has length L3. So these are given by N1, N2, and N3. Okay? And what we are going to do is make in each piece a uniform subdivision so that I get N1 number of elements in the first piece, N2 number of elements in the second, N3 number of elements in the third. So the total number of elements, if you see, will be equal to N1 plus N2 plus N3 if all these partitions are distinct. Okay. Now you see that in case one of these lengths or two of these lengths becomes 0, then this partition, even though we specify it, is going to be trivial information. We really will not use that information. Okay. What more do we need to specify? So we have specified all the information that we needed to have with respect to the domain, with respect to the material, with respect to the loading data, with respect to the boundary conditions, and here with respect to the number of elements we want in each of the pieces. The last thing that we need to specify is order of approximation. Small p. This we are assuming is uniform in the whole domain. Okay. So this is very important that we are going to specify this order of approximation to be uniform. We need not do that. We could specify different orders of approximation which can also be easily handled, but let us stick to this, that we are going to fix this order of approximation to be uniform. Okay, tell me that for the problem that we have written, that at least I have drawn on the blackboard, for that problem, what is the weak formulation? So the weak formulation will come out to be integral from x0 to xm, okay. According to the figure on the board, I will have E1 A1x du dx dv dx, okay, plus integral xm to x1 e2 a2x du dx dx, okay, is plus I will have integral of x0 to x1 k0 uv dx. So this is the part due to the spring, the stiffness part due to the spring. This will be equal to integral x0 to x1 f v dx. Okay. Now we have from the figure we have on the blackboard, we have an end load at the point x0. So that which is a tensile load, so it will be Q into, this will give work, Q into V at x equal to x0. Now at the other end, at x equal to x1, if I look at the end there, so I will have, if I look at this end, let me draw here, end x1, here I have K1 and initial compression delta 1. So if there is an initial compression delta 1, there is a further displacement of this end due to the applied forces, okay, as a reaction to the applied forces of amount U at L. So the spring actually compresses by an amount delta 1 plus U at L. So the total compression is delta 1 plus U of L. So the force applied by the spring is back on the member is P equal to minus K1 U at L plus delta 1. Now you see U at L is an unknown. So this part minus K. So let me first write it here, minus K1 U at L plus delta 1 multiplied by V at L. Okay. Now this part minus K into U of L, because it is in terms of the unknowns, I am going to carry it over to this side. Okay. And I am going to leave, so this into VL obviously. I am going to leave minus K1 delta 1 into V of L on the right hand side, while this part goes to the left hand side, because we are collecting all the unknowns on the left hand side. Remember this part, because this is going to be important as far as applying the boundary conditions is concerned. Similarly, at the end 0 we can do the same thing, where this end load Q can be now given in terms of the compression of the end x0. Okay, if I had a spring load there. Okay. So let us now see if this is my weak formulation. So in the weak formulation, which we could also derive using the variational principle. Okay. Oh, something else is missing here. Here we have not added the part due to the point load at point x0. So V at xp. So this part has to be added to the load vector side. So if I look at this weak form in its complete entirety, so it will be x0 to x1 E1 A1x du dx dv dx plus integral, sorry, x0 to xm, here xm to x1 E2 A2 of x du dx dv dx plus I will have K1 U at L V at L. This is equal to integral from, okay, plus I will have to add another part. Let me add, plus the part due to the spring x0 to x1 K0 uv dx. This will be equal to the load part integral x0 to x1 fv dx minus, so the right hand side will be integral x0 to x1 fv dx minus q into v at x0 minus K1 delta 1 V at XL, okay, plus P1 V at XP. So this is going to be our complete weak formulation or variational formulation, whichever way we decide to obtain it. Okay. And you see that these things should reflect in what we are doing in the program. So in the program, if you see, we are going to do the integration piecewise for these material constants, because my material constant is changing. So I have to go from x0 to xm, from xm to x1, and this will be anyway added from the boundary condition. This is not a problem. This part, since we are doing this piecewise, so I could do this x0 to xm, xm to x1. Again, it can be done piecewise and do the same thing. Here also in the load, I am going from x0 to x1, which means I can do it x0 to xm and xm to x1. And this part is from the boundary condition, this part is from the boundary condition. This I will have to add as the extra part due to the point load. Okay. So with this in mind, what we have developed till now as far as reading the data is concerned is going to be used. Okay. So let us now, once we have read the data, then what is the first thing we have to do? First thing is, given that data that we have read, we have to make the mesh. Okay. So let me So here, in order to make the mesh, we have said that as far as the computer is concerned, it has these points x0, x1, x2, x3. Okay, with length L1, L2, L3. So how do we go about constructing the mesh? So we said that we want a certain amount of partitions in each piece. So let's say in the first one I am putting 3 elements. So here I am going to put 3 equal elements. So here n1 is equal to 3. Let's say n2 is equal to 4. So I want to put 4 elements here. And let's say n3 is equal to 2. So I put 1 element here. Okay. So we should be able to construct these partitions using our program. And along with these partitions, we should be able to construct the coordinates of these nodes that we have created. So nodes, how do we number the nodes? We are going to say this is going to be node 1, this is going to be node 2, 3, 4. So we are going to number them sequentially. 6, 7, 8, 9, 10. Okay. So this thing should be possible while we are making the mesh. So as we are numbering the nodes, we should be able to give the coordinates of the nodes. So what we are going to do is, we are going to first say that let total number of elements in the mesh be given by the parameter NELEM. That is the total number of elements. First we are going to initialize it. Further, we are going to say that let the total number of nodes in the element be given by n node. We are going to initialize this also. These things are very important. Initialization of these quantities is very, very important. Now, you see that the way we have written the program, we have to know what material properties to use in a particular element. If I am interested in this element, how does the computer know what E to put there, what A to put there? So somehow I have to inherit that information for each of the elements from somewhere. So now, what do we say? That we are going to have an ID or a pointer or an indicator of which material domain a particular element lies in through this vector imat id. This is an integer vector. So this we are going to set. This is of size so we will fix some total number of elements. Let's say we say that the maximum number of elements in the mesh cannot be more than 100. So we will make this vector of size 100 and initialize all the entries to 0. Okay. Now what? So now what we are going to do is, further we will have the nodes of each of the points also initialized to 0. Also, we will have another information which we need. We will say we will create this array nodes we will make it this is okay. This is also initialized to 0. So all entries of this array, which is, if you see, this is element based. So if the total number of elements is 100, so this is 100, 2 array. All entries of this is also set to 0. So these are all the initializations that we will have to do. Okay. So after this initialization, now what we are going to do is we are going to construct the nodes. So what we are going to do is, the first node is given the value x0, which is equal to 0.0. Okay, and I am going to set, because I have already created this node, n node is equal to 1. You see what I am doing is I am incrementing the total number of nodes in the mesh as I am making the nodes. Okay. Now, if L1 is greater than 0, if L1 is equal to 0, I don't do anything. If L1 is greater than 0, then I find the mesh size, because it's uniform meshing, in this piece given by L1 divided by N1. Okay. Then for I equal to 1 to N1, that is, I take all these partitions. What do? I am going to increment the number of nodes, and I am going to say is equal to xn node minus 1 plus h. So what I have done is, given the first node, which is x1, I have created the coordinate of x2 is equal to x1 plus h, and so on. I construct all the n plus 1 nodes in this piece. Okay. Now, as I am constructing these consecutive nodes, I am also incrementing the number of elements. So I am going to say any LEM is equal to any LEM plus 1. That is, two consecutive nodes have formed an element in between, and I am going to say nodes any LEM comma 1 is equal to n node minus 1 nodes any LEM comma 2 is equal to n node. So I am telling what are the two n nodes for this particular element. Okay. Then I am going to end this loop. What I have done in this piece, I have found the mesh size in the piece, looped over the nodes in the piece, found what are the nodes, constructed it, and so on. Then I'll repeat the same process for L2. So we'll say if L2 is greater than 0, then I'll find H is equal to L2 by N2 and continue. Similarly, okay, and similarly I'll do for L3. Okay, for each of the piece. Now, while I am constructing the elements, let me see here. While I am constructing the elements, I am also going to check whether the first point, that is the x2, if you remember, x2 and x3, whether the first point is due to a material interface or whether it is due to a point load. Okay. If it is due to a material interface, then we know that L1 is from x0 to x2. So here I am going to give IMAT ID of element is equal to 1 or 2, depending on where this interface is. So at least here, depending on what this flag was. Okay. So this I am going to appropriately assign. At least in the first piece, it is always going to be the element, the material 1. Okay. So this way I continue. Here also I am going to assign while I construct the nodes. So construct nodes. Elements and then connectivity and then material information, which material domain it lies in. So if in this case for L2, we know that L2 actually goes from x2 to x3. So if x2 was a material point, then here my IMAT ID of all the elements here will be equal to 2. If x2 was xp, that is, it was a point load point, not a material point, then it remains as 1. Because the material is not changing, only the point load is being applied. And so on we continue doing. So this gives us all the information about the mesh, the elements, so the nodes, their coordinates, connectivity, number of elements, all this information comes out at the end of the program. Okay. So this is the very important component of the preprocessor, that is, we have made the mesh and all the relevant information that has to go with the mesh as far as our computations are concerned. So we will continue with this in the next lecture, and we are going to now talk of how to construct the degrees of freedom information for the given mesh for the given order of approximation. And from there we will continue further, talk about assembly, solvers and so on. Thank you.